Hello everyone, my name is Marcelo Coelho, and today I'm going to present the work that I did during my Master's at PUC-Rio under advisory of Professor Marcelo Coelho. It's called Experimental Analysis of Gas Condensate Flow in Porous Medium. So first we need to think about the world energy demand. Here we have two images from BP Energy Outlook, and in the first one we got the primary energy consumption by fuel, and then the second one is shares of primary energy. We have the oil in green and the gas in red, and we can see that for the year both of them are going to increase. But now if we pay attention at the second image, we can see that the share of oil going to decrease in the next years, and the gas is going to increase. The gas is going to have the second highest increase, only behind this renewable energy right here in orange. But if we check 2030, we can see that the gas share is going to be 2.5 times higher than the renewables energy. So now we are finding reservoirs at high pressure and high temperature, and some of the time we can find a reservoir that has a temperature that is higher than the critical point temperature. So we can have a gas condensate reservoir. So in this case, we have here a phase diagram. So in this case, we have the temperature of the reservoir between this critical point temperature and this pre-condensate temperature. So we are in this region in the middle. So checking this black line over here, it represents the reservoir. We have at the top the initial reservoir condition, and at the beginning we have only gas in the reservoir. And soon as we start to produce, we decrease the pressure, and we reach this blue line over here, this dew point line. And at this point, we have the first droplets of liquids coming out of the oil. And if we continue to decrease the pressure due to this production, we will reach this green line and then this purple line. And at this purple line, for example, we have 10% of liquids and 90% of gas. And if we continue to decrease the pressure, we are going to increase the liquids formation and then decrease again, going back to 90%. So due to that, we have some production issues. One of them is this condensate blockage right here in green, because this region around the wellbore, it has the lowest pressure in the reservoir, and that will reduce the reservoir production and can lead to some financial problems. Here we have two images for us to imagine better the phenomena. At this first image, we have the reservoir at high pressure and high temperature. So we have the matrix and the gas it's in this white part, and we can see that the gas can flow very well in the reservoir. But if we decrease the pressure to a pressure that is lower than the dew point line pressure, we will have the liquid formation. And we can see that the liquid accumulates and blocks the gas path, reducing the production. So the goals for this work are first to implement the pseudo-steady-state method, use the gas condensate, evaluate how gas relative permeability behavior in a porous media, and evaluate pressure condensate formation and gas velocity effects on relative permeability in two rock samples. So to start, we need to think about the mixture that we are going to use. So we need a mixture that has a gas condensate behavior, and since we're going to work in a lab, we need that the pressure and the temperature that they wouldn't be very high, and if it is better if it was a low complexity mixture, so we choose ethane and pentane. Here we have the phase diagram for our mixture. We can see that in all moments the pressure is higher than 950, and the temperature that we are going to use in the experiments is 80 degrees Celsius. and the mixture is 85% ethane and 15% pentane. And we also can see that we can reach values of liquid formation as high as 30%. So we wanted the two rock samples with different porous media structures, one with a homogeneous porous media and the second one with a heterogeneous porous media. So we choose the sandstone and the carbonate. Here we have two images from Rio College. In the first one, it's an image for sandstone, and we can see that we have very uniform pore size distribution, and that gets very clear if we go and check the second image. For the carbonates, we have huge pores and small ones as well. Here are our rock samples characteristics. We have two rock samples with almost the same size, very near porosity, and a slight difference in the permeability. The sandstone is 86 millidarcy and the carbonate is 160 millidarcy. So now I'm going to talk about the experimental setup that we built. We choose the pseudo-steady-state method. We have two cylinders. The first one, cylinder B, is our cylinder with our mixture at high pressure and high temperature, so it's only gas. And this gas cylinder right here, cylinder A, it's the gas that was produced, and its condensate, it's kept in this phase separator right here. The score holder keeps our sample at high pressure, and we have a pressure transducer here and the other one right here, so we are able to measure the pressure difference in the sample. And we have here this reducing valve. As I said, we have a mixture at high pressure. This mixture goes into this reducing valve. The pressure is reduced, and we have from this point gas and liquid flowing together. So as we can see, it's a closed system. The mixture didn't come out of the setup in any moment, so we have the same mixture for the first experiment and the last one, a single mixture, and it's inside of the oven, so we can keep the temperature very constant during the experiment, and we choose the injection at constant pressure and the production at constant flow rate. So how it's going to happen? We will set the pump B to work at constant pressure and pump A to work at a constant flow rate. So pump A will increase the cylinder volume and will decrease the pressure. It will need for cylinder B to inject the mixture to keep the pressure high, and it will start to produce. It ends when cylinder A is full. We close all the valves, stop the pump, and we have also a method to generate the same mixture with the same proportion again and bring it back to cylinder B. So now I'm going to talk about the results that we got. This is the single phase experiment that we ran to check if we built the experiment correct. We choose the carbonate sample to do it, and it's an open flow, so the reducing valve was not set, so we have only gas during the whole experiment. And at low flow rate, we got pressure difference linear, as we can see, and at high flow rates, we didn't get linear anymore due to some inertial effects. So here we have the gas relative permeability for our rock samples. We have the sandstone in blue and the carbonate in yellow. We can see that at low flow rates we got very close values for both of them, and as we increase the flow rate we increase the gas relative permeability. That was because the condensate that was blocking the gas path was vanished as we increase the pressure. And we see that at high flow rates we decrease the gas relative permeability, and we can see that the carbonate got higher values than the sandstone. That was because it's porous media structure with huge pores and its higher permeability. So from those goals that I talked at the beginning, we were able to accomplish them. And as final remark for this work, we could see that when we got low flow rates, we could increase the gas relative permeability as we increase the flow rates, and the gas relative permeability in the carbonate was higher, and at high flow rates we could see some inertial effects that reduced the gas relative permeability for both samples. I would like to thank you all for the attention and have a great day.